Hello everyone, and thanks for coming to the third video of this series. In the last video, we presented a very powerful experimental technique that allows us to tell whether the charged carriers that dominated the transport properties are electrons or holes, that is, the Hall effect. In metals, there is normally one type of them, depending on the sign of the curvature of the band structure at the Fermi level. In semiconductors, however, both of them can be present, and therefore both of them need to be considered to understand the transport phenomenon. Today, we will study the concept of pure semiconductors, also known as intrinsic semiconductors, and provide a deeper understanding on the conductivity and the dependence on the carrier concentration. So let's get started. Insulators and semiconductors have a lot in common. In terms of the band structure, at zero temperature, both of them have their Fermi level lying in between a filled band and an empty band, and neither of them conducts electricity. The difference between them is the size of that gap, the energy distance between the bottom edge of the upper band and the top edge of the lower band. In insulators is much bigger, about several electron volts. And as you know, this is in stark contrast to what happens in metals, where the Fermi level lies inside one of the bands. If it lies within the top one, electrons will dominate the transport phenomenon. If it lies within the bottom one, it will be the holes. Now, the hallmark of semiconductors is their peculiar behavior when we consider non-zero temperature. As we increase the temperature, the gap is not small enough to prevent some partial occupation of the higher band and partial depletion of the lower band, as prescribed by the condition of thermal equilibrium. In this context, I would like to bring a question on the table. At zero temperature, the actual position of the Fermi level is somewhat arbitrary. It should be somewhere in between this energy gap, but for that reason, we normally locate it right in the middle. But as soon as temperature is non-zero, the position of the Fermi level must be consistent with the number of electrons and holes that we have at zero temperature. In other words, the number of electrons in the upper band should be equal to the number of holes in the lower band. So, in this context, is the Fermi level still right in the middle of the two bands? Okay. This is the central question of this video, and to find an answer to that question, we first need to compute the number of electrons, which is given by this formula. The integration of the number of accessible states weighted by its thermal distribution. Here I have defined EC as the band edge of the upper band. The Fermi distribution here takes this form. At room temperature, which is about 25 milli-electron volts, the exponential factor is normally much larger than 1, because energy gaps in semiconductors are typically 2 orders of magnitude greater. Thus, the Fermi distribution is approximately given by this expression, this exponential, which, by the way, is the Boltzmann distribution. On the other hand, we saw in previous chapters that a free electron model, in free electron model, the density of states takes this form. Thus, to compute the number of electrons in the upper band, we need to compute this integral. Now, it's time for some mathematical jiggery-pokery. We need to perform this change of variables, which fixes the argument for the square root, and also the lower limits in the integral. After this, we need to perform another change of variables, which fixes the argument of the exponential. All we have left is an integral from 0 to infinity of this that can be actually solved analytically. And it gives exactly square root of pi divided by 2. By the way, I'd like you to try this integration just to train your mathematical muscle. Okay, after this, all we have is the temperature dependence of an effective density multiplied by set an exponential form. Okay, what about the number of holes? To compute the number of holes, we are going to repeat exactly the previous calculation step by step. Here, we need just to bear in mind that the thermal distribution for holes is 1 minus the thermal distribution for electrons. Now, the exponential in the denominator is much smaller than 1, and therefore it can be neglected. With this expression in mind, together with the density of states for holes, we arrive to this integral. Now, this is another exercise for you to try. Apply the very same change of variables that we have discussed earlier to obtain the number of holes, and the final result should look like this. And effective hole density multiplied by a certain exponential factor. Okay. Finally, we need to equate the number of electrons and the number of holes, and let math speak by itself. There are some factors cancel out, and taking the logarithm on both sides of the equation, we get an expression of EF as a function of the temperature. And here is the answer for the question I brought on the table a few minutes ago. As temperature rises, the Fermi level shifts linearly towards the band where the effective mass is smaller. Okay, this is the take-home message for today. However, before finishing, let's make a couple of comments. The first one being, we can express the number of holes and electrons as a function of the size of the gap. For these, we are going to square the number of the electron hole density, and because they are equal, we can express it as a function of the product of them. These will eliminate the Fermi the Fermi level from this equation, and after taking the square root, we have this exponential dependence of the electron density on the gap. Okay, we can still make a second note regarding the conductivity, because in pure semiconductors, both electrons and holes participate in the transport phenomenon. So we can define a phenomenological scattering times for electrons and holes, tau E and tau H respectively, and express the charge currents in terms of these properties. These should be proportional to the electric field, and the constant of proportionality is precisely the conductivity. Okay, this formula, however, does not apply to all types of semiconductors. Why? Easy. Because semiconductors can be doped, and we can add electrons and holes to these materials, thereby shifting the Fermi level at will. This property has made it possible a truly technological revolution of the 20th century. And for this reason, doped semiconductors, also known as extrinsic semiconductors, will be the topic of the next video. So, until the next video, goodbye.